Hello, everyone. Thank you very much for coming along this afternoon. My name is Ian Robinson, and I'm a principal graph and time series architect at AWS. And I'm joined this afternoon by Ken Hawthorne, senior backend engineer at Epic Games, to talk about how Epic have used time series data and Amazon Timestream to improve player experience across their entire catalog of games. So there are two parts to this talk. I'm going to be talking first. I'll do a little introduction to Timestream, to its overall architecture, some of its scaling characteristics, and some of the features that we've introduced over the years, and in particular, some of the features that we've added into the service this year. But that's really all background then for Ken, who'll be giving us a deep dive into how Epic have built a scalable solution for deriving customer insight from the playtime of millions of gamers. So Timestream was launched just over 3 years ago in 2020. And since then, thousands of customers, such as Epic Games, and NetScout, Experian, Prime Video, have used Timestream to build time series solutions across a wide variety of use cases and verticals. So these include things such as device monitoring and alerting, security analytics, user sentiment analysis, and video stream quality monitoring. Now, all of these use cases have several characteristics in common. Firstly, they tend to require a very high rate of ingest. So you may have millions of devices, tens of thousands of users or user sessions, and all these things are generating tens or even hundreds of metrics every few seconds or every few minutes. So that can translate into billions of time series, so you've got very, very high cardinality time series, and trillions of events a day. So very high throughput ingestion. On top of that, as you're ingesting that data, you need it to be available almost immediately for querying. So this is something that distinguishes a time series workload from a more traditional analytics workload, where you can very often ingest a very large volume of data, but it's often using a batch-oriented technique, which means that that data can be several seconds or several minutes out of date. That's not appropriate for a time series workload. If you're doing real-time monitoring, you want the data that's being generated right now to be available right now for analysis. Another requirement for a lot of workloads is flexible schema evolution. So you likely want to add new types of entity or add new attributes to existing data so that you can extend the kinds of analyses that you do. Now, in the relational world, that will often involve a very costly and time-consuming schema migration. But again, if you've got a real-time monitoring solution, if you've got a time series workload, you very often can't afford any downtime. You don't want to have to pause ingestion or querying in order to update that schema. So you need to be able to evolve your schema over time so that you can ingest and query the new side by side with the old. And then when it actually comes to conducting analyses or querying that data, you'll likely want to go both broad and deep. So you'll do fleet-wide aggregations over short and large time ranges. But then if you spot something of interest or some anomalous behavior, you want to go deep. You want to look in specific detail at a particular entity or some fragment of a specific time series. So how does Timestream address these kind of needs? So this diagram, this is a kind of overview of Timestream's overall architecture. And the first thing to point out is it's completely serverless. There are no instances for you to provision or monitor or manage. It's designed so that ingestion and storage and querying auto-scale completely independently of one another and driven by your specific workload needs. So it can scale to ingest gigabytes of data every minute and query across terabytes of data in seconds. Each of these layers is architected to be highly available and fault tolerant. And the query and the ingestion layers dynamically allocate resources depending upon your current workload demands. So if you've got a particularly bursty workload, for example, say you want to ingest or add a new set of devices into a fleet, well, that ingestion layer can very quickly scale up to address that increased and higher write throughput. Or if you're running a large global public event and you want to monitor user sentiment in real time, that query layer is going to be able to add new resources dynamically in order to scale out your analytical queries. So this is the ingestion layer. You write data to Timestream through its write endpoint, and that data is made immediately durable across 3 availability zones within a region. Timestream deduplicates your data upon ingest based upon the timestamp and the dimension names and values and a measure name. And it uses first writer wins insert semantics. So this is part of that deduplication process. So first writer wins insert semantics. But you can, if you want, apply last writer wins or upsert semantics on a per write basis using versioning. So this makes it really easy to accommodate late arriving data. You know, if you're ingesting some metrics and then some metrics arrive a little later, perhaps a device has gone offline and then it comes back online and starts sending metrics again, you can apply those over existing records, update existing records, simply by providing version numbers with those writes. This is the storage layer. So Timestream has 2 different stores. It has a memory store and a magnetic store. So most of your data, typically all of the data that's being generated immediately, will be ingested through that memory store. So that memory store is designed for very high throughput ingestion. You know, it can scale very quickly to accommodate ingesting gigabytes of data a minute, trillions of events a day. So it's optimized for high throughput ingestion and very fast point-in-time queries over very recent data. And then the magnetic store is optimized for larger scale analytics over larger data sets and longer time ranges, and also for low-cost, long-term storage. So that magnetic store can scale out to store petabytes of data very, very easily. Now, the data itself is tiered from the memory store into the magnetic store. So you get to supply a data retention policy to the memory store, and once the data ages out that memory store, it will be tiered automatically into the magnetic store. And you can do that on a table-by-table basis. So different tables within Timestream, you can supply different retention policies. Similarly, you can apply a retention policy to the magnetic store, and if the data ages out of the magnetic store, it's automatically deleted. And finally, with regards to the storage, Timestream provides exactly for that kind of flexible schema evolution. So you've got a couple of very simple abstractions, the database and tables have columns, but you don't have to define that table schema up front. Instead, Timestream will infer the table schema based upon newly arriving data. And if the structure of that data changes over time, Timestream will automatically update that table schema to accommodate it. So this allows you, for example, to roll out a new set of devices that emit data with a new schema, whilst continuing to ingest and query data from old devices with an old schema. Right. No interruption to the service, no pausing ingestion or querying in order to accommodate those changes. And at the bottom here, we have the query layer. So here we've got what we're calling an adaptive query engine that can query across those 2 stores. So you don't really have to worry about where that data resides. You just write a query, supply a time range, a time predicate, and Timestream is going to go and figure out where that data actually resides, and if necessary, fetch it from both stores and join it together. And it does that using a custom index that can partition the data and assign it to a specific tier. And then at query time, it's very easy, based upon the predicates in your query, for it to be able to find the relevant tiers and the relevant partitions to fetch exactly the data that it needs. So even if you've got petabytes of data going back over many years, if you're supplying a query that is really only focused on 5 minutes worth of data, Timestream is very easily going to be able to find the relevant partitions, fetch that data, and process it. And using this index, it not only knows how to find that data based upon those details, it can also estimate the resources necessary to process the data, ensure that those resources are provisioned, and then process the data in parallel. So I just want to spend a little bit more time talking about that indexing and partitioning scheme, because this will help you understand in a moment some of the changes that we've made to the ways in which you can model data and partition it. All right. So this diagram here really is a kind of conceptual view of Timestream's partitioning and indexing scheme for a specific table. So you can see it's a 2D space. So we have time along the x-axis, and then on that vertical axis, there's a measure value that you supply that helps us partition the data. So we're partitioning it by time and also by some measure value that you're responsible for supplying. And then you can see that that space is further divided between those two different stores, the memory store and the magnetic store. So at query time, the engine is going to be able to go to the index, identify the partitions along the time axis and the partitions along the y-axis, and find exactly the data that it needs, retrieve it, estimate the resources necessary to process it, and then process that data in parallel. So this is what is happening when you supply a query. Your query is going to have a where clause, so it's likely going to have a time predicate, some kind of time range. And then ideally, if you've supplied a dimension predicate that matches that measure name, we're going to be able to calculate the intersection of data necessary to find the relevant data. Now, Timestream can automatically partition and tier your data, but up until earlier this year, it was down to you to supply this very specific measure value that we use to partition the data on that vertical axis. And that's a kind of bit of extra overhead that for a lot of customers has added quite a bit of complexity to their solutions. I'll try and help you understand why that is. So I've got a Timestream table here with just a few records in it. You can see that each record has got a couple of dimensions and a couple of measures, and then there's this special measure name column. All right. Now, if the values in that column are very low cardinality, if there's just a handful of unique values, and you've got many billions of rows in that table, we're not really giving Timestream the opportunity to finally partition that data. Okay. So you can see a query at the bottom where we're supplying a time range, a time predicate, and we're also filtering based upon some measure value. But if we've used a very low cardinality value here, then it's likely that Timestream is going to end up scanning far more data than is absolutely necessary to compute a result. And that's going to make queries slower. You know, we're having to find more data and process more data than is strictly necessary. And that's actually going to be more costly, because one of Timestream's pricing dimensions is the amount of data scanned on a per query basis. So what we've tended to recommend historically is that you supply a value in that measure name column that is based upon a very high cardinality dimension that you often use in your queries. So if, for example, I've got a device name here. If a lot of my queries end up filtering by device name, then that's a good candidate for creating that measure name value. However, that measure name column can only support 8,192 unique values. So you might have billions of rows, but you can only have 8,192 unique values. So really what we've recommended is that you take that high cardinality dimension value, hash it, and then mod it by 8,192. All right, so that way you're getting a reasonably even distribution across all of the partitions. But you can see here how that adds all of that additional complexity into your solution. So we've got a query now, a slightly revised query, where when we're filtering by measure name, we're having to do that calculation. We're having to hash the value and then mod it. And that's on the read path, but you're also going to have to do that on the write path. So when you're inserting data, it will be necessary to calculate those values so they get inserted correctly into that measure name column. Right. So that's a kind of bit of additional overhead, a bit of additional complexity, which historically has proved a bit of a stumbling block. All right. Fortunately, this year we've introduced a new feature called customer-defined partition keys, and I'm going to talk about that in a bit more detail a bit later on. But that kind of eliminates a lot of this complexity. Simply by specifying a partition key, based on a high cardinality dimension, Timestream will automatically partition your data. It simplifies the queries and it simplifies the model enormously. But if you didn't know how to do this in the past, you'd often end up scanning more data and having more expensive queries. If you did know to do this, you had all of that additional burden of calculating the values on both the read and the write path. So that's the overall architecture. And this is some kind of indication of some of the scaling characteristics that arise from that partitioning scheme and the dynamic allocation of resources. So this chart is based upon some experiments that we did whilst improving some of the performance of Timestream. And here we can see 3 different data sets that are being ingested. And the ingestion rate is varying from 1 terabyte a day all the way up to 22 terabytes a day. So for the largest data set, we're ingesting around about 3 billion events per hour. And then the bars here represent the performance of a set of queries against each of those data sets. And it's a mixture of queries. It's a mixture of alerting and dashboarding and analytics queries. And what you can see is that those interactive queries scale very well even as the data set size grows. So as we move from left to right on that chart, we're seeing an up to 22x increase in the data set size, but the overall latencies for some of the longer running queries is increasing by no more than 5x. Right? So even as your data set size grows, with an appropriate partitioning scheme and the ways in which Timestream dynamically allocates resources based on its understanding of the needs of a query, we can scale very well for very large data sets. Okay, so that's the architecture and some of the scaling characteristics. I just want to talk now about some of the ways in which the service has changed and evolved over the last few years. So, as I mentioned earlier, it's just over 3 years old, released in 2020. And since then, there's been a continuous stream of new features, enhancements, and performance improvements. So this very busy little diagram just gives you a sense of some of the different things that we've achieved over the last few years. I'm not going to talk about everything in detail. What I do want to do is talk about a couple of the features that were released over the last several years that have made a big difference to the way in which customers develop Timestream solutions. And then I'm going to talk in more detail about some of the releases from this year. But one thing I do want to say is that all of these things we've been able to introduce it into the service without any interruption to customer workloads. So if you've got an existing Timestream workload, you can immediately take advantage of new features without having to take any downtime, without having to pause ingestion or querying. So the first feature that has made a big difference to the way in which customers develop Timestream solutions is multi-measure records. So when we first introduced Timestream, its data model was really optimized for IoT use cases. Okay? So with an IoT use case, you've got lots and lots of devices that typically are emitting a single measure or observation at different intervals. And so with a single measure record model, each row contains a single observation, a single measurement. It may have multiple dimensions, but it'll have a single measurement. But in 2021, we introduced a second data model that uses multi-measure records. So with a multi-measure record, each row can contain multiple measurements. And that's ideally suited to use cases where the thing that you're observing emits multiple metrics at the same time. So you think of something like a DevOps use case where you may be managing tens, hundreds, thousands of servers, and each of those servers is emitting multiple metrics at the same time. Things like CPU, memory, disk I/O. Well, now with the multi-measure record, we can store all of those measurements for an individual server, all of those measurements captured at the same time. And as you can see from the diagram, the storage and the representation format for multi-measure records is much more compact than that for single-measure records. And we're doing that by eliminating a lot of duplicate timestamp and dimension data. And because we've got a more compact storage representation format, that reduces storage costs, but it also reduces query latencies. We're having to scan and fetch far less data in order to compute a result. The multi-measure model also helps simplify queries. So I have a query here against a single measure table. Yep. And what we're doing here in the query is simply comparing two different measures, CPU and memory, to determine at each interval which of these is the bottleneck. But you can see if we were using the old single measure model, the first thing we have to do is create a couple of common table expressions to align those measures. And it's only in that select statement at the bottom where we can actually compare them and determine, each instance, which of those two measures was the bottleneck. If we look at how this is represented, or the kind of query that we write against a multi-measure table, it's a lot simpler. And that's because those two different measures or measurements are just different columns in the same row. So no need for a common table expression. So these queries are a lot easier to write, and they're a lot easier to understand. And what we found when working with customers that, and we tend to recommend multi-measure by default now. There's really no good reason for you to adopt the old single measure model. It's still there in the service, but by default, you should really be choosing to use the multi-measure model. And we found that across the board, it tends to reduce storage costs, reduce latencies, both on the write path and the read path. And it also reduces the amount of resource that you have to dedicate in your application to get data into Timestream. So if you can get more measures, more observations into a batch of records because of that more compact representation format, then you don't need to use as many resources on the client side to push all of that data into Timestream in parallel. Okay. The second feature that we've introduced in the last few years that's made a big difference to the way in which customers develop solutions is scheduled queries. So you often find when you're building a time series application that you need frequently to access things like roll-ups or aggregations, or you need to downsample data, particularly if you're building visualizations or dashboards or reports. With scheduled queries, you can build these data transformations that will pre-compute those results on the scheduled basis that you specify. Now, those scheduled queries, they're just standard SQL queries. It supports all of the variety of SQL that Timestream supports. Timestream has a number of very specific time series data types and functions. All of those are supported with scheduled queries. And like the rest of Timestream, it's completely serverless, scalable, and highly available. And as you're computing these results, and you're doing this on a scheduled basis, you're incrementally refreshing a target table. And the results in that target table, the table itself is a lot smaller typically than the raw underlying data. So for many customers, it makes sense to keep that table of pre-aggregated results in the memory tier for a lot longer and to tier out the raw underlying data from the other tables more quickly. So they might keep the raw data around for just a couple of hours and then tier it into the magnetic store, but they'll keep the aggregations in the memory tier where it can be accessed very, very quickly, these kind of point lookup queries, accessed very quickly, and they'll keep that data around for a lot longer, perhaps several days or even weeks. And the kind of benefits accrue as you introduce multiple dashboards or reports or visualizations. If they're all very, very frequently querying the aggregated results, you're going to see a magnification in the benefits of using scheduled queries. So this is what an example scheduled query looks like. It's a regular SQL statement. The only difference is it has this scheduled runtime parameter, which is a timestamp that is supplied by Timestream every time it invokes the query. And using that scheduled parameter, you can effectively define a windowed function over your data so you can incrementally compute results and refresh the target table. Okay, so just fast forward to this year, and these are the areas that we've focused on really over the course of this last year. So 3 areas of focus: data protection, enhancements and new features, and performance improvements. So at the beginning of the year, we introduced integration with AWS Backup. So that's a policy-driven, centralized data protection solution, and it's applicable to a lot of different data services and stores within AWS. So by way of this integration, we're effectively allowing you to align your data protection strategy across all of your important stores within AWS, including Timestream. In terms of features, we introduced a batch load feature that will allow you to ingest large volumes of time series data from CSV files that you have sitting in S3, and an unload keyword that allows you to write the results of a Timestream query back to S3 so that it can be shared with other services. I'll talk about both of those in a bit more detail. In March, we added additional CloudWatch metrics that allow you to better monitor the service usage. And in the middle of the year, we introduced a service-free trial, and that's got a generous budget for storage, querying, and ingest. And then in terms of performance enhancements, we introduced optimizations around single series queries. So if you've got a query that's targeting a single series, and by that I mean something like it's targeting a single device or a single user, we've introduced optimizations around that to be able to compute the results very quickly. And then we introduced customer-defined partition keys to address that overhead of having to compute those measure name values. And again, I'll talk about that in a second. So batch load allows you to ingest large volumes of time series data from CSV files in S3. For very large data sets, you'd likely end up splitting that into multiple files. We've kind of got the recommended file sizes there. It's very easy to create a batch load task. You can do it through the console, the CLI, the SDKs. And you can load the data into an existing table or into a new table. The most important thing you have to do is to define a mapping between the columns in your CSV file and the timestamp, dimensions, and the measures in your table. There's one thing to be aware of. If the timestamps in your CSV files fall outside the retention period for the memory tier, remember that memory tier is really optimized for very high throughput ingestion. If the timestamps fall outside of that period, then Timestream will try and write that data directly into the magnetic tier. But the magnetic tier supports a maximum of 250 active partitions per database. So you can only be writing to at most 250 partitions at a time. So if you've got a very large ingest and it's writing to more than 250 partitions, it can be throttled and it can potentially cause the job to fail. So you can monitor the number of active partitions using this CloudWatch metric. But this is a constraint that applies at the database level, not the table level. So you can't get around it by trying to ingest in parallel into multiple tables. Okay. Unload is a keyword. It's the flip side of batch load. Effectively, it's allowing you to take the results for computation and write those results to S3. This is probably my favorite feature of the year, because the moment you can get results into S3, it opens up a whole bunch of data lake and ML and AI and ETL use cases. Just a kind of serendipitous reuse of all of that analytics data. You can write in both Parquet and CSV format. You can choose to compress the data and partition it. You can introduce a partitioning scheme there. And you can encrypt it on the server side using Amazon S3 keys or using your own customer managed keys via the key management service. This is what it looks like. Again, a regular select statement, but we've now surrounded it with the unload keyword. We're specifying where we want to unload that data, and then we're supplying some details around the format, the way in which we want to partition that data in S3, and the way in which we want to compress it. And then the last important feature of the year, customer-defined partition keys. So I talked all about those issues with having to calculate that measure name value. With customer-defined partition keys, that problem pretty much goes away. You choose a high cardinality dimension, and again, it's something that you're frequently using in your queries, so you need to base it upon your access patterns. You choose that, and then you define the partition key at table creation time. So you're still not having to define the entire schema up front, but you are having to define a partition key. And then as the data is ingested, Timestream will automatically partition that data on your behalf. So again, we've got that simple representation of the 2D space and a query here. The time range predicate will help us identify partitions along the x-axis. And if we've supplied another filter that matches the partition key, that will help us identify partitions along that vertical axis. And that makes it really easy to compute the intersection of data that we need to fetch. And the overall result here is it makes it easier to model the data. No need for that measure name column anymore. You're simply defining the partition key when you define the table, and it simplifies the query. So again, we're no longer having to filter by measure name. We're simply filtering by the device name and supplying a time range. Okay. All right, so that's general introduction to Timestream, overall architecture, some of the scaling characteristics, some of the ways in which the features have changed the way in which people work with it over the years, and some of the new stuff from this year. I'd like now to welcome Ken to the stage, who's really going to get to the meat of the session, which is Epic's experience with Timestream.
Great, thank you, Ian. Hi, everyone. As Ian mentioned, I work for Epic Games, specifically on the Epic Games Store. Now, if you're not fully plugged into the gaming space, I'll give you a little bit of an overview of what Epic Games does. The foundation of the company is the Unreal Engine. It's, put simply, a 3D creation tool that's used in everything from AAA video games, like the Final Fantasy VII Remake series, all the way to hit cinematic productions like The Mandalorian. You'll even find it in some manufacturing visualization software, like the kind you'd find like on McLaren showroom. We're also the makers of Fortnite, one of the world's largest games. It's since evolved into an entertainment platform that hosts massive interactive events. In fact, we set our record for highest concurrent users just a few weeks ago, and we've got a huge upcoming event this weekend that we hope are going to challenge even that. In addition, most relevant to today's talk, we operate the Epic Games Store, which hosts all the offerings I just mentioned, as well as providing an ecosystem for third-party developers to publish and distribute their own games. We also run extremely popular free game giveaways weekly, as well as daily during our holiday and summer sales. So what does Epic Games have to do with Timestream? Well, today I'm going to give you a look into how the Epic Games Store, EGS, implemented Timestream for our player ratings page. Then I'm going to walk you through the steps we took to optimize that solution for the intense load we ended up having to handle. So to give some background for this feature, Epic wants to know how players feel about their games. And perhaps more importantly, we want to provide a way for others to benefit from that knowledge share. Now, reviews are the most common form of this for storefronts, and Epic's implementation looks like this. You'll see a broad score with some callouts for popular tags that users have given the game. We populate this page by directly polling users. After they finish a play session, we'll do some analysis behind the scenes, and then based on the user's eligibility for the game they were playing, they'll get some quick toasts like these the next time they log in. So I buried the lead a little bit there in that description. The complicated part isn't the aggregation and showing this page. It's actually the eligibility piece that we're going to get into today. We're trying to make sure that we get results that are relevant to other users. Now, determining the right user is pretty complicated, it turns out. Do we ask any owner of a game to review it? Well, I just mentioned the EGS weekly giveaways, which makes that pretty complicated. When anybody can own the game, how do we know their opinion is informed? Do we check if they've recently played the game? Well, just booting the game is pretty similar to that first problem, unless we combine it with some other metric. Or do we require a minimum playtime, like we do for the refund process? Returning players make that a little bit convoluted, because maybe they're coming back for a new patch, or they're coming for DLC, and they've got tons of playtime in the past. Essentially, the patches can change the relevance of users' opinions over time. So what kind of patterns are we looking for to determine eligibility? Well, some ideas that we had were maybe they played a certain amount of time, but in the last X number of days. Or maybe they played a certain amount of time, Y days in a row. Or maybe they launched the game more than a certain number of times in the last Z days. So I'm sure everyone here can kind of poke holes in using a single one of those metrics, and I'm even more sure you can come up with a bunch more axes to attack. But eventually we did settle by basing poll eligibility on some sort of playtime patterns, which we configure game by game. However, querying playtime patterns was going to be a little bit more complicated than our existing implementation, which just tracks a running total for a user's playtime. So before we get into the Timestream bit, let's quickly go over the pre-existing flow we had for tracking playtime. Our client is the Epic Game Store launcher. It periodically submits playtime data to a REST API in our library service, which just gobbles up the requests. As long as the request looks well-formed, we take the data and let the client get on with its business. The library service does some light validation and then places it on an SQS queue for asynchronous database ingestion. We have a Lambda, which picks up that playtime record. It does some slight aggregation and checking validation with the database to make sure we haven't stored too much duplicate data. And then it updates the raw playtime table with the new raw playtime values. I want to note here that we use Lambdas quite a bit in our backend for this store. The load from the launcher can be a little spiky. We have all the load problems of a normal retail outlet combined with an entertainment venue. So we've got sales and holidays, but we also have huge blockbuster releases. So Lambdas are a really easy way for us to fine-tune throughput for specific pieces of our flow. So speaking of scale, what does our normal playtime traffic look like? So I'm going to give you EGS stats as of December last year, because that's what's public. But please be assured the last month of record-breaking Fortnite releases has, we'll say, challenged us far past these. So EGS has over 230 million accounts using the PC launcher, which is the client that tracks playtime. It maintains roughly 68 million monthly active users. We have a spiky but pretty predictable daily usage pattern that looks like this. It takes in around 83,000 requests per minute, with an average record size of around 250 bytes, spiking up to 2.3 kilobytes and upwards. Which means we're processing around 23 megabytes of data per minute, or roughly 33 gigabytes per day. So as far as data load goes, we're looking at a smaller overall volume than most time series situations, but our data source count is very high. So with a baseline understanding of our architecture and our load, our next step is selecting a time series database that'll get us what we need to analyze users' playtime. So what did Epic need? First and most importantly, we wanted to reuse as much of our code as we could as possible, preferably the exact same code that we had for storing playtime. Timestream allowed for this. We actually just created a database with the same object with almost no modification. We also wanted quick retrieval of total playtime. We were looking for the last 2 weeks at the start. Our initial tests were outside of our hopes for a synchronous API response, but Timestream ended up being well within the bounds for an asynchronous postback type solution that we'll get into later. And then we wanted to store at least a year's worth of data. We wanted to do something like a year-end user highlight, like if you've got a Spotify account and you see your year in review. We wanted to do something like that. And this is the piece where Timestream really shined. The magnetic storage configuration made this part borderline trivial. We also wanted to query the yearly data in seconds, not minutes. And when testing Timestream, we saw that queries across an entire year were around 6 times longer than the 2-week queries we were using as a baseline. So we had 26 times the data for 6 times longer queries, still well within our under a minute stipulation. So things checked out there. And then finally, we wanted as many ways as we could to tune performance to our load and cost needs. Our asynchronous handling of queries via Lambdas would provide the usual Lambdas knobs for concurrency and throughput. And our proof of concept we did showed that grouping several Timestream queries into one could actually be done with pretty low performance hit. So in short, Timestream met pretty much all our desired criteria. So let's get into our initial design and see how Timestream factored in. So here we are looking at the initial infrastructure I showed you before. And as I mentioned, we knew from our Timestream research we'd be able to use the same data object. So we added a Timestream database right alongside our current DDB that was holding raw playtime. We wrote to this at the same time as our current DDB write. Our ratings and poll service would be the client that would be submitting requests for playtime. So we added a playtime query route alongside our current API, put those requests from the poll service onto an SQS queue, and created a new Lambda that would execute each Timestream query as it came in. We placed the results from the Timestream query back on an SNS topic, which the ratings and poll service was subscribed to. So this asynchronous postback-like flow that we have for the poll service wasn't what we'd pictured at the start of the project in our ideal world. But what began as a concession to our large data set, it ended up being pretty great for tuning purposes and super valuable for some changes we made that are coming up. But before we get to that, what did this initial implementation get us? OK, so put it bluntly, it got us throttled, and probably all of US East. This is our formal apology to US East. Our poll service traffic was hitting us a lot harder than we expected. We did the math for capacity, but we made a lot of assumptions about how it would play out at that scale with Timestream. So what we saw in production was 7 days worth of raw, deduped playtime data ended up being around 63 gigabytes total. And on average, our poll service was hitting us at around 7,000 requests per minute, spiking up to 12,000. What did that mean for Timestream? It meant that we were searching for all data points across 63 gigabytes over 100 times per second, spiking up to around 200 times per second. In essence, our query load was massive relative to Timestream capacity. Now, time series databases are generally optimized for finding a metric at a specific point in time, like if I wanted to know the temperature of this room last Friday at 2 p.m. But we were finding all data points across all available time and summating it and stretching the implementation a little bit. However, part of our criteria for selecting Timestream was we knew we'd be able to tune stuff to fit our load. So we have knobs. Let's get into which ones we turned and how we did it. So the first change we made was the size of the database. Kinda. For the API we were offering, we conceded that we didn't need every point of data that we were querying. Essentially, we worked backward from the business need that we ended up having and toned down our implementation to the minimum granularity that we could get away with. Ultimately, we settled on aggregating for a day's worth of playtime to support what the ratings and poll service was asking for the most. So we made a new database that would hold new daily measurements for playtime. We would still keep the raw database because we would want to be able to adjust the granularity if we needed to later. The aggregated data object would be the exact same structure and use the same queries as the raw data. So all we needed to do is swap the Lambda data source and use the same queries. But how did we populate the new aggregate database? Well, fortunately, we didn't need to set up any more of our own infrastructure to do it. We can use scheduled queries. So I think the name scheduled query downplays the functionality quite a bit. What it's actually doing is a straight up data transformation. It's a data transfer cron job. However, scheduled queries, as innocuous as they may sound, are still database operations, and we can still get ourselves into trouble. But to prevent this, we broke out our cron jobs into several queries, and they downsample across various time periods. So our current day's data is predictably the most volatile, so we run the current day aggregation every 15 minutes. And then the data from 7 days ago is the least volatile. We run that every 12 hours. And then each day in between is tuned to a recurrence equal to its volatility. And remember, we are doing this without modifying any of the queries in our Lambda. We just swapped a config value and pointed at the aggregate database. So with everything else unchanged, what did this look like for database size? We'll start with the raw playtime table I showed you earlier that was sitting at around 63 gigabytes for a week worth of data. We'll run our scheduled queries for ingesting data to our aggregate database. You can see the 7-day aggregations every 12 hours, and then interspersed with the transformations all the way down to every 15 minutes. Which gets us our aggregated playtime table with a final size of around 500 megabytes per day. So with the raw data totaling around 9 gigabytes per day, we go to a data set that's roughly 1/18 the size of the original set, all at the cost of losing granularity that we weren't using in the first place. Again, keep in mind that we changed nothing in the application code. So by setting up some quick aggregation jobs and another table, we reused all of the other code and saved around 90% in database costs, in addition to reducing the query rate to something that didn't get us completely throttled. Now, as effective as downsampling was, we didn't stop there with our changes. You may remember I teased earlier that asynchronous flow ended up being pretty advantageous for us. And that's because it let us utilize message batching. I also mentioned at the beginning in our proof of concept, we saw that very little performance difference when compounding multiple queries into one. So let's attempt to add batching to the Lambda and group several completely unrelated requests and queries. We start off by reconfiguring our Lambda to take in a batch of messages from the playtime request queue. The Lambda puts all the batched accounts and games into a single Timestream query and runs that against the aggregate database. Once we have the query result back from Timestream, we'll separate them all back out into their individual messages. We place them back under the response postback topic to kick off the ratings and polls flow, with the calling service being none the wiser that we batch their queries. The response time difference ends up being negligible. The code for this looks really simple at the query level. Instead of querying for a single account and game, we modify our where clause to include all the accounts and games from our batch of messages. The small change ended up letting us reduce our query count to roughly 1/23 the original volume, which actually opened up way more query throughput than when we were just doing one-to-one queries for requests, which in turn allowed for a larger Lambda concurrency range for us to tune. It had the add-on benefit of lowering our Timestream costs by another 10%. So those two changes, downsampling and query batching, did the majority of the work for reducing our costs and increasing our throughput. But there's one more change we made that I want to get into. And that's using multi-measures and the measure name column to partition our data. So the TLDR for this slide is that Timestream tables, in Timestream tables, the measure name column is used for partitioning. That's point blank. In our initial implementation I showed you, we only had a single measure, playtime, that we were specifying as the measure name, which makes sense because playtime is what we were measuring. However, if we only have a single type of measure, following along here, and we aren't changing the measure name column, we aren't using Timestream's partitioning. For Timestream implementations with multiple metrics in a single table, this happens automatically. Like if you have a system that's measuring CPU memory, CPU temp, all at the same time, it makes sense to partition based on whatever you're measuring, whatever you're searching on. Now, we knew that our account playtime data would never be relevant to each other. So we're going to manually manipulate the measure name to influence Timestream's partitions for our search dimension. In our case, we changed our queries to look like this. You can see in our where clause that we actually seeded the measure name with the first 3 characters of the account ID dimension. This partitioned our data based on the search dimension and decreased our query times even more. Now, if this sounds familiar, that's good because it means you were paying attention while Ian was talking and during his description of customer-defined partition keys, as it's basically the same exact thing. We implemented this manually before it became a full-fledged feature of Timestream, but you get to use this in your own projects for free. So those 3 changes cover what we've already done. What do we want to do but haven't gotten to yet? The first up is to deprecate the manual partitioning done via measure name that I just talked about. We would love to swap over to the new user-defined partition keys. It'll make queries look a lot cleaner, and it'll give us a bit more granular partitioning. We'd also like to increase our playtime accuracy by running the downsample queries a little bit more often. Our scheduled queries that you saw before are fine-tuned for what we're able to get away with, but we definitely consider bumping up the frequency if we knew it wouldn't throttle us. And like I mentioned at the beginning, we'd like to retain yearly data. Now, the hard part for this, the reason we haven't gotten around to it, is because setting up privacy measures for account IDs is actually a little bit more difficult than the Timestream part. We can't store data that users don't want us to, so we need some kind of hashing solution before we can store the data. The Timestream part is actually really easy, though. It's a single config value for magnetic storage, and we're in business. It's just as easy as sampling 7 days, 14 days. We just changed that value to 365. And then finally, you saw that our raw playtime Timestream database is a duplicate of our pre-existing DDB table. So deprecation of a duplicate table seems like a logical next step. But we're not going to do this. Dynamo is actually really great for retrieving single running tallies, where Timestream is optimized for more investigative tasks. So replacing the Timestream or the Dynamo table that maintains that running tally would just be asking for inefficiencies. So the heuristic here is to use Timestream for investigative tasks. So in summary, we started with Timestream for several reasons. The first one, and most importantly, it let us reuse our existing ingestion flows and objects. Secondly, it had reasonable query time for an asynchronous implementation. We loved the ability to tune magnetic storage, and it made retaining long-term data super trivial. It also had exceptional speeds for querying a year's worth of data, and we knew that there was a lot of flexibility with our architecture for tuning performance and cost based on our load at the time. And ultimately, we achieved success not by nailing it on the first try, but by iterating and incorporating feedback from our initial design. We added scheduled queries to downsample our data. We batched our requests to take advantage of performant compound queries, and we partitioned our data a little more effectively. So with just a few changes, we went from a completely throttled single query jackhammer to a solution that lets us understand how users are playing their games daily, utilizing all the same objects and data that we had before, not to mention room to grow with new features. So hopefully our learnings will help you create your own Timestream solutions. And to that end, I'm going to pass it back to Ian to give you some more resources to get coding.
Wonderful. Thank you. Thank you very much, Ken. OK, yeah. So we're pretty much ready to wrap up. It's really over to you now. So if you've not used Timestream before and you're interested in investigating it, you can get started today. As I mentioned, there's now a free tier, and that's got very generous budgets for ingestion, storage, and querying. Over the last few weeks, we've been publishing a series of different blog posts, lots of use cases, and lots of details around some of those new features, including unload, batch load, and the customer-defined partition keys. And we have a wide variety of tools and sample applications in our AWS samples GitHub repository. So that's it. Hopefully you've got a sense of how Timestream works, how we achieve some of the benefits, how we scale using that serverless and decoupled architecture, some sense of its scaling characteristics, and the way in which we've invested and changed and introduced new features. And it's just been a pleasure to hear how Epic have used it and how they've evolved their solution and what they're planning to do in the future. So thank you very much for coming along, and enjoy the rest of the conference. Thank you.